Welcome everyone on the 4th Quantum Research Seminar Toronto QRST. And today we have two guests, speakers, Nana and Diego, and I leave it to Alba.
Well, let me just summarize very quickly what are the rules of this meeting. So the two talks will last 25 minutes approximately each. And after each talk, we will have 5 minutes or so for questions. And if we are running out of time, you can continue asking questions in the chat or just wait until the end of the seminar so we stay a little longer with the speakers and we can continue discussions. And yeah, I think it's this more or less everything. We are recording it, of course, and the videos will be uploaded in our YouTube channel. And yeah, I think that's more or less everything. So let me introduce you, Nana Liu. She's a tenure-track associate professor and PI of the Quantum Information and Technology Group in Shanghai, Jiao Tong University. And she's working on quantum algorithms and other quantum protocols. She received her doctorate in 2016 from the University of Oxford and was a postdoctoral research fellow at the Center of Quantum Technologies in NUS and in Singapore. And her research focused on employing quantum resources for both quantum computation and sensing, and also lies at the interface between quantum computation, security, and machine learning, which will be useful in building a future quantum internet, which is very trendy these days. And she will present, her talk is titled, Taking Advantage of Noise to Protect Quantum Machine Learning Algorithms Against Adversaries. So Nana, the floor is yours. Welcome and thank you for your presentation.
Thank you so much, Albert, and thank you for having me here. I mean, I wish I would meet you guys in person. Well, good morning. So today I'd like to share with you some recent work on the developments at the interface between security questions and learning problems when we start having access to quantum resources. So an example of this is when we have a quantum device that may be used for a machine learning problem like classification, but is compromised by the presence of adversaries. So an adversary who might want to induce misclassification in your protocol. And our questions that we may ask is, can we place theoretical limits, general theoretical limits on the vulnerability of these algorithms? And if so, like what mechanisms can we have to help us extend the robustness of these algorithms? And given that noise is something that is very prevalent, and certainly in current quantum devices, is there a way of using this to our advantage? Right. So in helping us maybe smear out or maybe mask the effect of these adversaries. And all these questions, they come under a new area called adversarial quantum learning, which combines the areas like security, quantum resources, and machine learning. And just to give you guys a little bit of context, so as I was talking a little about the quantum internet, so I started thinking about these questions because ultimately I'm very interested to know what are the things we can do on a future quantum internet. So not just having classical devices which are interconnected with each other, but having quantum devices with quantum communication channels. So what are the most appropriate algorithms to perform in protocols in these type of settings? And if we take inspiration from what we do on classical type of network, then actually machine learning algorithms are very appropriate for these settings because data here are often naturally delocalized in a network, and they're often in these distributed settings. So we start thinking about like video surveillance data or sensory network data in a classical setting. And it's even more important in the quantum setting when we start sharing quantum data, that we start having quantum resources that actually create these quantum data in different geographical regions. And as soon as you start having more than one party, like you do in a network, you're going to have security issues. And when you have security issues, it turns out that noise, the concept of noise is in fact very intimately connected with the idea about security. In quantum technologies, we're very worried about noise. It has a negative connotation mostly because it disrupts our protocols. But in the classical realm, it turns out that noise is often exploited to help us protect information. So whether it, or not it's encoding data or to preserve the privacy of the data. So for example, if we add noise to the algorithm itself, and we actually see an example of this a little bit later on. And another way to think about the intimate connection between noise and security is that we can think about noise maybe as a way of masking the presence of an adversary, because somehow fundamentally an adversary, so an agent that poses a security risk, is really a worst case scenario type of noise. So, so if you're not given the noise model at all, and you want, a theoretical guarantee to protect yourself against this noise, what is that limit? So that's kind of equivalent to thinking about an adversary. So there's really more of a continuum now of problems between problems we care about in the presence of noise and that of having adversaries. So not, two entirely separate regimes. Okay, so there's more of a smoother continuum. And all these questions, they belong in a larger picture of this area called adversarial quantum learning. So it's right at this junction between three different areas of security, quantum information, and machine learning. And so what I'll be talking about today is really just a very small beginning in trying to explore these larger context questions. So I hope this just to be kind of a starting point rather than just pointing out like a nice result. And why do we expect that, this to be a fruitful exploration? Well, so we know there's really a lot of overlap between quantum information security. I mean, the first viable quantum technology is really in the realm of quantum cryptography. And there's already a very large, overlap of, questions that people are asking, between quantum information and machine learning, which is what you guys do in Toronto, right? So, either using, quantum devices for classical machine learning problems, or, using machine learning techniques for quantum problems. And, collectively, that is called quantum machine learning. Okay, so you guys know a whole lot about this. But there's this other area which I think is under examined, certainly from the quantum community, and this is the overlap between security questions and machine learning. So you're either focusing on using classical machine learning problems for security, or what's becoming more popular recently, looking at the vulnerabilities of machine learning algorithms themselves, and they all fall all under this umbrella term of adversarial machine learning. So it's a very big community classically, but has not received a lot of quantum attention. And everything kind of, in the middle of this Venn diagram, we call adversarial quantum learning. And, we see there's really a lot of, possible questions we can ask in this area. So where do we start? So one big motivation that I had when thinking about these problems is really noticing how many of these quantum algorithms that we look at for machine learning, they really rely quite heavily on speedups as a motivation. But, having been in the computer science department for a while now and, talking to classical computer scientists, a lot of these classical machine learning people, they're often not all that particularly interested in computational speedups. So, and they have a lot of other concerns. And in particular nowadays, their main concern is that of security. So then the natural question is, can we exploit quantum resources to help with security advantages? So for example, in quantum machine learning. In a similar way that quantum information has really contributed a lot to the area of cryptography. So this is the main question that we want to ask. And then it naturally leads on to more specific questions, which is, can we explore the vulnerability of quantum machine learning algorithms to adversaries? And since you were saying before that adversaries are somehow like a worst type of noise that you can have, can we then exploit a noise to help us actually protect against these adversaries? And so far, a lot of the work that has been done on this, well, there hasn't been a lot of work, firstly, but the work that has been done is, very specific to, particular algorithms. So, taking specific algorithms like PCA or K-means clustering, like what Nathan and Ram has done in their earlier work, and finding more robust versions of these. And it follows very much the trend of classical machine learning as well, taking up, specific machine learning algorithms and using a very, algorithm-specific technique of making them more robust. Okay, and then later on, looking at some classification algorithms, quantum devices, and looking for adversaries for that from Dong-Ling Dan and his group in Tsinghua. But what we'd like to do is to step back a little bit because, we're interested maybe in more foundational questions and say, well, are there more general bounds that we can think about, that is maybe independent of the particular details of the algorithms? Because not only would we like to address the question of what is the robustness of, say, a quantum classification algorithm against general adversaries, but are we able to improve the robustness in a natural way? And by natural, meaning that we don't want to think of new robustness techniques for every new algorithm that comes out. Okay, so something that is slightly more general. And at this point, you'll be asking, well, all right, so you keep talking about adversaries. What do you mean by an adversary? So if we look at the lineup of the factory lineup of machine learning, it goes something like this. Okay, so you have many different elements in there. You have your raw data that you start off with. then you might want to extract some key features, pre-process some data, then you assign your learning algorithm, your model, and then once you have your model, you have your prediction step. So an adversary, in principle, can really come in at any point, along this factory lineup. Okay, so all these are legitimate type of attack models, and they can come, and they can be classical or quantum, and they can come during training time or testing time. So either during training, so when you're deciding the parameters of your algorithm to use, or during testing time, once you have your algorithm and you're inputting the data that you actually want to use your algorithm on. But what we would like to start concentrating on today is this particular testing time type of adversary, which are called adversarial examples, because it provides one of the clearest demonstrations of a really big problem that they have in classical machine learning. They have entire conferences just on this particular problem. Okay, so I'll tell you guys a little bit about this. But first, what do I mean by this particular adversary? So say, Alice already has a quantum device to perform a classification task. Okay, so the only thing that she's lacking are quantum states that she wants to classify. And these quantum states might be coming from Bob. So now our question is, what if Bob's states, so not Alice's algorithm, but Bob's states may be compromised in some way by an adversary, which is actually inducing misclassification when Alice tries to classify them. Okay, so this is our general setup for today. And this is the general setup of adversarial examples. And this is probably one of the earliest famous examples of an adversarial example of this panda. So neural network classifiers are well known to be very, very good at image classification. So, if you look at the panda on the left, they're usually quite good at classifying correctly. But it's been discovered to have an Achilles heel, because it's possible to engineer specific perturbations. So if you look at this, what looks like a random image, it's not. It's a specifically designed perturbation. But if you add it to the picture, you end up with a panda that, to us looks more or less identical, but now has been misclassified by the neural network. So before it was a panda, and now it's a gibbon. So this is an example of a white box attack. So the adversary who designs this perturbation has access to the parameters of the classification model. But it's also possible to have black box attacks. So meaning, the adversary can just design noise and they can't see, inside this classification model. So you have, pictures, the original picture on the top, and then, slight perturbations, adversarial perturbations on the bottom. So in the first line, we see they're being correctly classified. But once we start adding in these adversarial perturbations, which to us, they're not doing anything essentially, but it's being misclassified by the neural network. And this is not just a few fun examples, but it's actually a very generic feature of neural networks, and not just of neural networks, but actually all other all other machine learning algorithms that people have been studying. But of course, neural networks get a lot more exposure because they're just so successful, generally. So it's generic behavior across classification models and across data sets, not just images, but audio data as well. So it's our task to really understand, what is really going on if it's really such a generic feature. And it's not just for classical machine learning, but we also have a lot of quantum examples. So these are quantum algorithms for classifying quantum data. So for example, asking if a quantum state is entangled or not, having algorithms for that. Which phase this quantum state may be in, or to decide if a particular quantum state is an unusual state or not, if it's an anomaly. But before we start, asking ourselves how to protect our algorithms, the first is we need to know our limits. Okay, so can we have some kind of idea, what the robustness of our general quantum classifiers is against these adversarial examples? So first, just having a picture of what classification is. So supposing we want to classify pictures of ants and cicadas. So points representing pictures of ants on the left and cicadas on the right. And suppose we already trained our model. So we already decided upon a decision boundary. So this is the line in the middle. And then if we're given a new data point, so this orange dot here, it's a new cicada picture, and we know that because now it's to the right of this line. But what do you do if you're an adversary? Okay, so we have the same picture, and if your new data point is very close to the boundary, what is your strategy as an adversary? So your goal as an adversary is to induce a misclassification. So because originally cicada, you want them to think it's an ant. but you also don't want to move very much because otherwise you'll be detected. So you want to move by a small amount to induce a misclassification. So the best strategy for you, in this case, is to move across the boundary slightly. Okay. And this already gives us a nice geometrical picture of what's going on, because it's saying the vulnerability of the algorithm really depends on the concentration of data that you have that you want to classify about the decision boundary. Because if you are very far from the decision boundary, no matter what you do as an adversary, you're going to get caught, right? Because in order to move across the decision boundary, you need to move by a large distance. So already this is pointing us to a geometrical way of resolving the problem. And the great thing about this geometrical way is now we're getting away from the algorithm-specific picture. Okay, so this is just really about dividing your space into different regions for classification. So for example, if we want to classify points on, say, the surface of the sphere, these little red points. The important thing to know about machine learning algorithms, that are trained on real data, is that there's always some region where you're going to be wrong. Okay, so there's no machine learning model that's completely perfect on every new piece of data that you give. Okay, so I mean, of course, it's always possible for it to be perfect on everything that you're trained it on, but then you have a lot of overfitting, and there's no guarantee that the next point that you give you're going to classify correctly. So there's also always this margin of error, okay, which is acceptable. So just for simplicity, I'm just going to draw this as a green blob. I mean, in general, it's going to be a much more complicated picture. And now let's say we want to classify the red point. So that's at the center of this orange dotted circle. So as an adversary, what is the strategy? Okay, so as an adversary, you want to move the smallest distance of this red dot so that it moves into this region of this green cloud. Okay, so it becomes misclassified. And the robustness of this is then quantified by the amount epsilon. So that if you say your model is vulnerable to these epsilon adversaries, what you're really saying is that you're taking the region that is misclassified, and then you're creating a region that's called the epsilon expansion of M. So you're taking all the boundary points of these misclassified points and moving them outwards by the amount epsilon, so that if your point lies anywhere like within this band of this epsilon expansion of M, then you can always find an adversary who moves by the amount smaller than epsilon, so induces a misclassification. Okay, so then, in other words, what we're looking for is the probability that you land within this banded region. Okay, so and here we can introduce the concentration of measure phenomenon. Okay, so a concentration function for geometries which satisfy something called the Levy families. So it has a concentration function y minus alpha, and this y minus alpha quantity represents the probability that one lands within this epsilon expansion region. And if you happen to be in the geometry, like spheres are part of this geometry, then if the concentration function follows the function on the right. So L1 and L2 are just constants, like depending on the specifics of your geometry, and D is the dimension of your data. So if your geometry, it belongs to these Levy families, then it means that as dimension increases, y minus alpha rate approaches 1 very, very quickly, meaning that you're almost always going to land within this epsilon expansion region. Okay, so what this is saying is that as dimension increases, then more likely than not, there's going to be an adversary that just by moving by the small amount epsilon, they're going to induce a misclassification. And it so happens that for SUD, and if you're Haar randomly selecting your state from SUD, then it satisfies this concentration function. Okay. And how do we use this result for our scenarios? Remember, our scenario, we have good Alice, okay, with her good quantum machine learning classification algorithm with some input state sigma. And then Bob comes along and wants to say, well, Bob can be used to prepare maybe this particular state sigma, okay, which originally had a classical description, but maybe Bob encodes it in a quantum state. But then something goes wrong. Okay, so either Bob is being adversarial and he's not giving the right state, or an adversary messes with Bob's data, so that instead of getting the original state sigma, now Alice gets the state rho that has only been slightly perturbed. So our first theorem for adversarial quantum learning is, so if sigma is some d-dimensional quantum state and a perturbation, sigma to rho occurs, and if the adversarial risk is less than r, so adversarial risk, the probability that you tolerate of being wrong, then this particular epsilon is upper bounded by this quantity on the right. So don't worry about any of the details. This is a very short talk. But the only thing I want you to notice is the quantity that in red. Okay, so you have a quantity that scales inversely with d, which is the dimension of the data. So what this is saying is that as your states become, as the dimensionality of your state increases, epsilon becomes smaller, so that it's more and more likely for an adversary to move by smaller and smaller amount before they induce a misclassification. So it becomes easier for an adversary to attack your classification model. And all these results here was really derived on having Haar random selection from SUD, because we're using a purely geometrical way of thinking about this, and we're saying with SUD then with our concentration results is taking all of SUD. Okay, so then we're selecting any random state across this whole geometry. But in realistic cases, you're hardly ever told to classify random state randomly selected from SUD. Okay, so what are the consequences of restricting your Haar random selection assumption? So supposing we're only restricted to a fraction k of the states. Okay, so we're selecting from k of the states from this SUD. Then we can generalize our adversarial learning model, where now k becomes part of your upper bound for epsilon, how much an adversary should move before they can already induce a misclassification. And don't worry about the details. What are the consequences? So as an example, so before we saw how highly dependent the size of the adversary is to dimension. Okay, so as you increase in dimension, then the adversary doesn't need to work nearly as hard, right, to induce a misclassification. But now what we see is that the dependence on dimensionality can completely disappear if we make k small as dimension increases. So for example, when we have low entanglement states. So and this really hints at maybe there's a fundamental trade-off between the security, like the robustness of the algorithm, and the knowledge we have about the input states that we start off with. So the smaller the k, somehow the more information we have about it. Okay, so now we see there's kind of this loophole, like in this generalized robustness, meaning that if we know something more about the algorithm, about the data that we want to classify, getting away from Haar randomness, maybe we can improve robustness. Okay, and we want to improve robustness in a natural way. Remember, so we don't want to go along the model-specific way. We want to find a method which works, no matter what kind of algorithm we're looking at. And this is where noise comes in. So the general idea is that noise provides a form of randomization. A randomization gives rise to a property called differential privacy, which I'll talk about. And this differential privacy is what gives rise to the robustness feature. And it takes us away also from the Haar random selection criterion. So the key results here are, if we add depolarisation noise in our quantum classification algorithm, and no matter what the specific details of the algorithm are, so long as we add in depolarisation noise, it can help to protect the privacy of our inputs. And having protection of the privacy of the input helps us to tame possible adversarial behavior. And as a result of this, taking a step towards thinking about introducing new figures of merit for quantum advantage in quantum machine learning. So now this is independent of speed up, but really more of a security advantage. So what is differential privacy? Okay, firstly. So suppose we have some data set X that we select from a group of people, and we apply some randomized algorithm on it. So everything here is classical right now. And now suppose we take away a person's data. Okay, so the total data set is now X prime. So what we mean by the notion of privacy is that we want the outcome of the randomized algorithm not to be greatly affected whether or not the person had their data in or had their data out. So meaning the probabilistic outcomes from X or from X prime, they only differ by this factor e to the power of epsilon. So if epsilon is very small, then they're almost identical. So then you have good privacy. So in other words, small epsilon means better privacy. We also have the quantum analog of this, so that instead of having the data X and X prime, we have quantum states sigma and rho. and where sigma and rho, they differ by a small amount. Okay, so the trace distance between them is upper bounded by some quantity, let's call tau d. And the great thing about quantum algorithms and why it lends itself so easily into this differential privacy formalism is that quantum algorithms, they naturally output, probabilistic outcomes. Okay, so whereas in the classical regime, you have to really engineer, you have to randomize your algorithm artificially, but with quantum, you get that somehow for free. Okay, so how do we apply this to a classification algorithm? Well, what is a classification algorithm? So let us take away all details about it. So we have the input as some, quantum state sigma, and then it's black box. Okay, so we don't worry about, what happens in the middle, and we just have an output. Okay, so we have, so if it's a single qubit measurement output, so, we say what's the probability of getting outcome 0 versus outcome 1. And, the outcome 0 can represent the probability that it's in class 1, and outcome 1 is a probability that it's in the other class. And if you want to open up the black box, so for example, a quantum neural network example, we can have that. But really, we don't care about the details right now. So how we apply this is that, so now we have, a quantum classifier, okay, where we really have very little information on what's inside the box. So therefore it's generic. So if we have, input state sigma that we want to classify, and we can have some ancilla state in there, and then all the black boxes in some unitary or some channel A. So the lemma that we have is that if we now add a depolarisation channel, so the orange blob over here, then the epsilon part in epsilon privacy has this expression. So the only thing that we need to know from this expression is that as p, so this is the amount of depolarisation noise, as p increases, epsilon decreases. So remember what we said before, smaller epsilon means more privacy. So this is saying as we start increasing depolarisation noise, we get more differential privacy. And furthermore, it doesn't matter where we put in the depolarisation noise. It can happen at the end, the beginning, in the middle, anywhere. But then you might, and here, for example, the blue part can be a quantum neural network classifier or anything you want. But then you might say, well, I mean, this is not very special because if you add in more noise and you randomize everything, of course you get privacy. You just get nothing, right? You just get everything that's maximally mixed. So the other thing to ensure, so in addition to getting more privacy, is that you want your algorithm itself to be useful. So here this is where we have the second lemma. So that if your circuit is used for classification, so what you can show is that under the depolarisation channel, the predicted class label does not change. So if you have infinite sampling, it does not change. But if you have finite sampling, the sample complexity only depends on the amount of noise. So we see that it scales inversely to 1 over p squared, where p is the amount of noise. But it doesn't depend on the size of the data. Okay, so you get the same class label. So what this is saying is that you get good accuracy, you get a good prediction without, so with more noise, you don't compromise on your prediction, but you also get the advantage of more differential privacy. Okay, and again, it doesn't matter where you place the circuit. I just have a couple more slides. I'm almost done. So now we have the central theorem, which says that if we have a noisy circuit, we have differential privacy, and if we add a little bit of an extra condition, which is related to getting us out of the Haar random condition, then we can guarantee robustness against an adversary. Okay, so this is the generic theorem. So I won't go into the details of this. I'm actually already out of time. But I'll give an example of how we can compare this to classical algorithms. So let's look at a very simple example. I won't go into the details, so let's just look at the picture. Okay, so we want to classify answer cicadas. And so let's say we have a simple model called like a linear kernel, and all that means is that there's kind of a straight line separation between these two pieces of data. So if you want to add in classical noise, you can do that if for linear kernels n equals to 1, or for a very high n. So in this case, your model can be a more more complicated, some polynomial way of separating these boundaries. So, and what you can show is that the robustness of these algorithms under this classical noise that you use to protect your algorithm, the robustness generally depends on your model parameters. So model parameters like n, how complex your decision boundary is. But what is really interesting about the quantum model that we have is that the robustness, so now it's instead of in terms of a length, a difference between x and x prime, of the classical data, it would be tau d. So this is the upper bound to the trace distance between the quantum states. And it's upper bounded by the quantity on the right. So b is just some constant, and then p remembers the amount of noise that we have. But what we do notice here is on the right, there's nothing there that depends on the details of your model. Okay, so n doesn't appear, it doesn't, no details appear there. What this is saying is that, adversarial robustness and quantum device can be independent of all the model parameters, unlike the example that we saw in the classical regime. And, we thought a lot about this, and I think one of the reasons is it could be that, with depolarisation noise, the outcome of the quantum classifier is independent of where the depolarisation noise is inserted. And it's not true for the corresponding classical Laplace noise that is used for classical differential privacy. So the general result is, okay, so we add noise, it gives differential privacy, and differential privacy gives rise to robustness. But how important is this idea of differential privacy? Can we have robustness with noise alone? So instead of going through differential privacy, we just go directly by restricting the Haar random condition. And I think this is something that we're looking at for future work. So we're working on this right now. But it really, opens the door to thinking about a lot of different mechanisms we can have a look at, and really exploring this connection between our security and noise in the quantum realm. So the take-home messages today, lessons are, so quantum classifiers are vulnerable to adversaries, just like with classical algorithms, and it depends both on the dimension and also the distribution from which we select stage one. And secondly, we can see how quantum noise can actually help us reduce this vulnerability in a way that is independent of the learning model. So looking at ways on how we can go beyond the just having speed up advantages, but also having these security advantages for quantum machine learning. And lastly, acknowledgements. So thank you so much for inviting me to your nice seminar, and thank you so much to my great collaborators on this. And these are the two papers that I've been talking about today. And maybe this is not the best time, for this slide, but whenever this COVID thing is over, please come and visit us in Shanghai. You're very welcome. Thank you.
Thank you, Nana. Sorry?
Sorry if I went a little bit over time.
No worries, no worries. So we are running out of time, but I think we have time for one quick question. So I just say that Matthias de Grote has asked a question before. Can the adversary always know where M begins and ends? Isn't that as hard as solving the whole thing? M is the misclassified region, I think.
Sorry, so what is the question? How do we know what M is?
So if the adversary can always know where the misclassified area is, begins and ends, if it has that information.
Yes, so that's a very good question. So at the moment here, we haven't provided a constructive proof. Okay? So this is a proof of concept that in principle, if we have an all-powerful adversary, they're able to move by this amount of epsilon. So this is why this is like a general limit to how far they can go. But it's true. So if you want to restrict the power of the adversary, then you have a different epsilon. Yeah, but here this is saying if we have an all-powerful adversary, then you can't do better than that, essentially.
Okay, thank you. And there are some other questions in the chat, so I think that if you wish, you can answer them in the chat or after the meeting.
Oh, right.
Because
okay,
we need to pass to Diego, otherwise we are running out of time. Okay.
Okay, cool.
And thank you again. It was a very informative talk and very interesting. So thanks.
Thank you.